Now, we know how to draw lines in R2. Basically, in the xy plane, if I have a point in the direction, and by direction we're typically thinking of the slope. So here I am in the xy plane. If I have this known point and I know it's going in that direction, my slope is like maybe over 1, 2, up 1, 2, 3, something like that. There's my slope, 3 over 2. Then I not only can I identify a second point if needed, but I can, with this direction based on the slope, I can now define exactly where my line is. Now we'll do something similar in R3. A line in R3 is determined by a known point, and I'm going to call that known point P0, which has coordinates x0, y0, z0, that's on the line, and the direction of the line. That's really all we needed here. And R2 was a point in the direction of the line. But the direction of the line in R3 is not exactly the slope. It's not quite the same thing. So let's go ahead and go draw a quick picture here. I'm going to say here's my point P0, which has coordinates x0, y0, and z0. Now P0 is going to be our known point. Now this line, I'm going to say, here's my line L. And I'm going to pick a point right here. It's an arbitrary point, P, which has coordinates x, y, and z. So P is an arbitrary point. On L, and of course P0 is also on L. Now with that, notice I have between P and P, or P0 and P, I'm going to say I have a vector that I can use here. I'm going to call this vector A. And vector A has representation P0 P. Now if my origin is, say, down here, then I can set up, say, vectors R0, which is going to be a position vector, of point P0, and vector R, which is going to be position vector of point P. So here's vector R0. Here's vector R. Now, I have this known point P0. All I need now to really find the equation of this line is to know what direction it's heading in. Because right now P0 is really the only known thing, and of course the origin. So I'm going to take this vector here. I'm going to say this is vector V. And vector V is going to be my direction vector. Notice that V is going to be parallel to the line L. Now, think about this for a second. I need to be able to describe any point on this line. I need this point, I need that point, I need that point. If we think about the triangle law, really, vector R can be written as vector R0 plus vector A. So I have R0, this position vector going from the origin to the known point. I add to it vector A, and now I am at vector R, or that's equivalent of vector R. So the tip of R is at this known point. So what that means is that there must exist MUST, got messed up a little bit. There we go. There must exist T, which would be a real number, such that vector A is equal to T times the directional vector V. So there's some value of t such that t times v will give me a. And obviously t, because it's a real number, t is a scalar. Therefore, I can write vector r as being r naught plus tv. Now, any point on the line, any point I want, can be described based on an appropriate value for t. Give me the right value of t, and this vector r would come out to here because a gets longer. Give me a larger value of t as compared to whatever would give me this vector. They're bringing a out longer, bring a out like out to here. So now my vector r is like this. So the tip of r now goes through this point. So for any value of t, like I said, I can get any value on this line. Now the way I'm thinking about this, or the way I have this written up, for t equal to 0, what I end up with is vector r is equal to r naught, which means I'm at this known point. So for t positive, I'm going in this direction, going in the same direction as v. And for t less than 0, my line's simply going in the opposite direction. Now, I'll leave that diagram there. Vector v is going to have components, say a, b, c. Therefore, t times v, remember t is a scalar, is going to be equal to ta b, tb, and tc. Just simpler scalar multiplication of vectors. Therefore, I can write vector r as being xyz, which is equal to x naught plus at, which is this component right there, y naught plus bt, and z naught plus ct, of course for t being a real number. Which leads me to a parametric representation. So parametrically, I could write this as x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. Now, what I've just done is this is in parametric form, this is the equation of the line L. And vector form, this is the equation of the line L. So this is also another representation of the line L. So there's a couple of different ways that I can actually represent this line L based on vector equations.